Welcome, everyone. Today, we are diving into a crucial topic for scaling your machine learning workloads, creating and managing components within an Azure Machine Learning workspace. Let's transition from isolated experiments to production-ready, reusable assets. Let's begin by defining what a component actually is. In Azure Machine Learning, components allow you to create reusable scripts that can easily be shared across users within the same workspace. Think of a component as a self-contained building block. During early development, data scientists often write long, monolithic Jupyter notebooks. However, when you are ready to prepare your code for scale and move your model to production, you need modularity. By breaking down your workflow into components, for instance, one script for data pre-processing and another for training, you ensure your code is standardized, repeatable, and easily shareable with your team. Ultimately, components are the essential puzzle pieces used to construct sophisticated, automated machine learning pipelines. Looking at this diagram, we see the transition from a traditional monolithic notebook on the left to a scalable architecture on the right. By refactoring our experimental code, we extract specific tasks into distinct Azure Machine Learning components, such as data prep, model training, and evaluation. These modular, independent components are then orchestrated together to form a robust, scalable machine learning pipeline, making our workflow production-ready. To effectively build a component, you must understand its anatomy. An Azure Machine Learning component strictly consists of three core parts. First is the metadata, which includes the component's name and version. This is vital for source control and tracking. Second is the interface, which explicitly defines the expected input parameters like your raw dataset or a specific hyperparameter and the expected outputs, such as evaluation metrics or the trained model artifacts. The third part is the command, code, and environment, which dictates exactly how to run your script and what computing dependencies are required. By separating these elements, your Python logic remains clean, and the Azure platform handles the complex provisioning of environments and data routing. This block diagram visually breaks down the three pillars of an Azure Machine Learning component. At the top, we have the metadata, giving the component its identity. In the middle, the interface acts as the contract, defining exactly what data goes in and what artifacts come out. At the bottom, the command, code, and environment layer tells the system exactly which script to execute and within what specific Docker container or software environment. How do we actually build these components in practice? To create a component, you need two fundamental files, a script containing your workflow logic and a YAML file. Let's say you have a Python script named prep.py that removes missing values and normalizes your data. You cannot just upload the script alone. You must pair it with a YAML file. Let's call it prep.yml. This YAML file is a declarative manifest. It defines the metadata, the inputs and outputs, and the exact terminal command required to execute your Python script. It also references the specific environment your code needs to run. If you prefer a pure Python approach, Azure Machine Learning also allows you to use a special @command component decorator function over your Python method to dynamically generate this YAML file behind the scenes. Here we see the component creation workflow. You bring your Python script containing the business logic, represented on the top left. You pair it with your YAML manifest, containing the configuration, on the bottom left. These two files merge to create the Azure ML component object. Alternatively, as shown by the dotted line, developers can use the command component decorator directly inside their Python code to bypass writing manual YAML files entirely. Creating the component files on your local machine is just the first step. To truly unlock their value, you must register them. Registering a component publishes it as an official, version-controlled asset directly into your Azure Machine Learning workspace. Why is this important? Because it enables collaboration. By registering a component, you make it accessible to other users in the workspace who can reuse your code in their own pipelines. You do this programmatically using the Python SDK. First, you use the load component function to read your YAML file into memory. Then, you use the create or update method on your ML client to push it to the cloud. This effectively creates an internal marketplace of reusable, vetted machine learning building blocks for your entire organization. Let's walk through the registration sequence. The local developer uses the Azure ML SDK to load the component via the YAML file. Once loaded, the developer pushes the object to the Azure ML workspace using the create or update command. The workspace acknowledges the registration, tagging it as version 1.0. Now, anyone else on the data science team can fetch and reuse this exact version-controlled component in their own separate projects. Now that we have registered components, we can build a pipeline. In Azure Machine Learning, a pipeline is defined as a workflow of machine learning tasks where every single task is a component. This allows you to arrange tasks sequentially or in parallel. You can even run different components on different compute targets. For instance, running data prep on a massive CPU cluster and model training on an expensive GPU cluster. To build this, we use the pipeline decorator in Python. Inside this function, you call your loaded components. The critical step is data routing. You take the output from your first component, say, the pre-processed data, and explicitly pass it as the input parameter to your second component, the training script. Azure ML handles all the underlying data transfer. This flow shows how components wire together inside a pipeline. The raw pipeline input data feeds into step 1, our prep data component. Notice the arrow connecting step 1 to step 2. We programmatically map the output of the prep step directly into the input of the train model component. Finally, step 2 outputs our ultimate goal, the newly trained machine learning model. The pipeline acts as the master orchestrator for this data flow. Defining a pipeline is great, but we must execute it. When you submit your pipeline to the cloud, it runs as a pipeline job. It is crucial to understand the hierarchy here. The pipeline job is the parent, and each component running inside it executes as a child job. This architecture makes debugging highly efficient. If your workflow fails, you don't dig through massive monolithic logs. You simply inspect the specific child job that failed to see if the data prep or the training component caused the error. Furthermore, pipelines are designed for automation. Instead of running them manually, you can attach a job schedule with a recurrence trigger. This allows you to automatically execute the pipeline job every night or every week, ensuring your model is always learning from the freshest data. Here we visualize the execution architecture. You can manually submit the pipeline or use a recurrence trigger for automated execution. The Azure ML orchestrator takes over, spinning up child job 1 and child job 2 independently. As they run, each child job streams its own success metrics or failure logs directly into the Studio UI dashboard. If the training job fails, you know exactly where to look without disrupting the data prep logs. Components are the driving force behind a successful MLOps lifecycle. In MLOps, we separate our work into an inner loop for development and an outer loop for deployment. Because components are modular and versioned, they fit perfectly into source control systems like GitHub. We implement feature-based development. No one is allowed to push code directly to the main production branch. Instead, if a data scientist wants to update the data prep component, they do it in a feature branch. Opening a pull request automatically triggers a GitHub Actions workflow. This workflow uses your updated component, runs the pipeline job in the cloud, and verifies the model's quality before a human reviewer approves the merge. This guarantees production stability. This flow illustrates our secure MLOps CI/CD pipeline. A developer updates a component in a feature branch and opens a pull request. This event triggers GitHub Actions, which automatically runs our Azure ML pipeline job in the cloud. If the pipeline succeeds and quality checks pass, the workflow pauses at a human approval gate. Once the lead scientist approves, the updated component merges to the main branch and deploys. Let's apply everything to a real-world use case. Consider Prosware, a healthcare startup that developed a diabetes classification model to help practitioners diagnose patients via a web app. Medical models often experience data drift based on the geographical population, meaning the model must be retrained frequently. By breaking their workflow into reusable Azure ML components, Prosware solved this scaling challenge. They created a standardized data prep component and a training component. Now, using GitHub Actions, whenever new geographical data arrives, the pipeline automatically runs, retrains the model, and updates the endpoint. Even better, because their data prep component is registered and modular, when Prosware decides to build a new model for heart disease next month, they can instantly reuse the exact same prep component, accelerating their time to market dramatically. In this final diagram, we see Prosware's scalable architecture. New patient data triggers a GitHub action, initiating the pipeline job. The data flows into the shared component for cleaning health data. Notice how this single, registered component branches out to feed both the diabetes model training component and a future heart disease model component. The newly trained model is registered via mFlow, seamlessly updating the live web app endpoint for doctors.